Hello, today I'm going to talk about vapor pressure and I'll be discussing something more about it like is vapor pressure dependent upon the quantity of liquid kept in the container, and I'll be discussing about total vapor pressure of two miscible liquids. So let's try to understand what vapor pressure is. So let's take our container first. Suppose that this is my container and it's closed from the top. Okay, and up to this point I've got some liquids in it. Okay, this is my liquid in it. So what is vapor pressure? This liquid is kept at certain, say, at a temperature, and what happens that uh, we have got molecules on the surface of the liquid. Suppose these are the molecules on the surface of the liquid, and uh, at any instant they get sufficient energy that they go into the vapor state. Since they are at a certain temperature and they are connected to the outside environment, so they might attain certain energy that is enough to vaporize it. So this will go into the vapor state. Suppose these are my vapors. Okay, so the same will happen with these molecules. Those are on the surface of the liquid, and we'll be having vapors. But at the same time, maybe this molecule, the earlier molecule which was there, might hit the wall over here, or might hit the liquid and might get attached to it once again, or might get stick to it once again. So what we can see is that there is a rate of change of vapor into liquid, and from vapor to the liquid, but the rate of change from vapor to liquid is more than the rate of change from vapor to liquid. Sorry, there's a rate of change from liquid to vapor is more than the rate of change of vapor into liquid. So what happens is that you know the the liquid changes into vapor. So this is how I'm going to represent it by a bigger arrow. Okay, and for that, from the vapor to liquid, I'll use a smaller arrow to show that the rate of change from vapor to liquid is slower than the rate of liquid to vapor. So a time will come when we have got more vapors in this space, and we'll be having more of the vapors so that they could stick onto the liquid once again. So since you have got more vapors, the probability that they will stick to the container increases and the rate equalizes. So this smaller arrow becomes equal to the bigger arrows. That means the rate of change of liquid to vapor and vapor to liquid are the same now. Okay. Now what if we have got the same thing? This is called as vapor pressure. The pressure that is exerted on the liquid at equilibrium. Now suppose that I take out some liquid. So for example, this liquid is water. So I have got the same container. But what if I take out some liquid from the container? What do we think will happen? You know, when now this vapor is creating, say, 50 mm of Hg pressure on the liquid or on the container. So suppose that this vapor is having a pressure of 50 mm of Hg. So what if when we decrease the volume of the liquid? It's quite certain that this vapor over here is creating some pressure that is equal to 50 mm of Hg. Now since we have decreased the volume, that will give some more room to the vapor to wander. Now the thing is that since we have got less vapors over here and it's got bigger space, now the liquid will start turning into vapor till it reaches the 50 mm Hg pressure. And besides that, when we reduce the volume, we have got a decrease in the pressure. Okay, because the same amount of vapor is given a bigger volume will exert lower pressure on the container. So as a result of that, we'll be having a lower pressure over here. In order to balance the pressure, it again vaporizes. That means the liquid over here again vaporizes so as to reach the equilibrium point, and again we attain the pressure that is 50 mm of a G. Okay, so there is a change in volume, and that volume resulted in more vapor formation, uh, and that created the same vapor pressure. Now, what if in the third case I increase the volume? Okay, so what we'll have, so here we are having more vapors. Okay, so more vapors. Okay, what if this volume, I mean say these vapors all of a sudden see a change, or a rise in the volume of the liquid. So in order to attain the same vapor pressure, the number of vapors has to be decreased. Otherwise, if the same vapor is contained in this given amount of volume, this volume, then it will result into a rise in the vapor pressure. So in order to uh, offset the change that is made by the addition of that has been made by the addition of volume, it has to reduce the number of vapors. So in that case, some of the vapors will go into the liquid phase, and we'll see decrease in the number of vapors so as to attain the same vapor pressure, and that is again 50 mm of Ag. So we can come to a conclusion that the vapor pressure is independent of the liquid that is present in the container. Okay, so why am I saying that? The reason is that uh, uh, we have got a container that is closed from the top. If we let the container open, then we'll see that all the vapors have gone. All the liquid has, since there is enough space, so we won't be having this forward and backward reaction reaching equilibrium, because since we have got enough space, so they will all vaporize into the atmosphere. Now, so what if we take two miscible liquids and the volatility of which are different? For example, say we have got a species A, means a liquid A, whose vapor pressure is 50 mm of Hg, and we take another one whose vapor pressure is 60 mm of Hg. Now, as I said, that it is independent of the amount of liquid. You take this these many liquid, or you take you know a liquid that is much larger or smaller than this, still it will create the same pressure on the container. So over here, suppose that I've got a liquid that consists of two different soluble, that is miscible liquids in it. Now, for discussion's sake, first let me close the volume given space. Okay, now for discussion's sake, say first we had only one A-type liquid in it. So the A-type liquid will go into the vapor state till it reaches 50 mm of Hg. Okay, 50 mm of Hg. So we are having more of the vapors over here. So let's take a different color for it. So we are having more of the liquids over here. Sorry, more of the vapors over here till it reaches a pressure of 50 mm of Hg. Now, what if I add the same A liquid in it? As I said, that it will only reduce the number of vapors, and so as to maintain the same vapor pressure. So even by adding more volume of this A liquid into the container, we don't see an increase in the vapor pressure. So what if we mix, say, this part of the volume with, say, B? So we are having now two different components which are miscible, and uh, since, and let's say from here we can say that B is more volatile than A. Okay, B is more volatile than A. Volatile. I'm so sorry about the handwriting because I'm doing it with the mouse and I'm not quite handy with it, so which is why, you know, you have to please bear with me. Now, what we can see over here is that we have got two different liquids. Now, B is more volatile than A. That means if we think B over here, if it goes into the vapor state with a different color, we can see that we'll be having the vapors of B into the given amount of space over here till it reaches equilibrium again. Now the question is that uh, how much vapor pressure we experience. See, had we had, you know, the whole, you know, volume of this liquid B, the maximum limit of vapor pressure we could have attained is 60 mm of J. Now, since we have got both the volumes of the liquid A and B, so we cannot exceed the vapor pressure that could be more than 60 mm of J. So from that we can say that the maximum vapor pressure which could be attained by this thing is 60 and the minimum is 50. So our vapor pressure will be the value which is greater than 60, which is greater than 50, but less than 60. Okay, because since if we had taken the container filled with half or whatever, you know, portion filled with the volume of B liquid, so we'll be having a vapor pressure that is 60 mm at J. So since we have both A and B, you know, both will vaporize and they will give vapor pressure that would be between 50 and 60. So if we could graph this thing, we could do it like this. Suppose that on the x-axis I've got the moles or the mole fraction of both A and B. Suppose that here I've got A, that is, you know, 1 means the complete, you know, it's the total volume is of A, and this point A is 0, A is 0. Over here B is 1, okay, and over here my B is 0. So what does that mean? That at this point B is 1 mole, the mole fraction of B is 1, means the container contains only B, and at this point the container contains only A liquid. Okay, now suppose that this part shows my vapor pressure, both cases. Okay, and if one is more volatile than the other, as we have seen it, suppose that this is my A. Okay, A, and the mole fraction of it is 1, so at this point it will grow from 0. The vapor pressure over here has to be 0 because there is no volume of A, so 0. Now since we go towards the left side, what we see is that we are having some fraction of A, you know, some mole fraction of A, and there are some more liquids. So suppose that it reaches this point, so this is my so I have to make it a bit smaller. Okay, it's a straight line, although it doesn't look like. And in this case, at this point I have got uh, B as 0, so I don't have any B in it. And this point, the B is, the container contains only the liquid B. So, and the mole fraction is 1. That means the container contains only B. So here it's 0 and starts growing up. It goes up to this point. Okay. Now what we see is that the point over here, as I said that this is the lowest point, means 50. We can have a vapor pressure that is at least 50. Okay, so if we keep moving towards this direction, so it's a straight line again, and so say this is my point which I'm concerned with. So at this point I might have some volume of A, so, and some volume of B. So see, from A0, so it's decreasing and reaches up to this point, and over here for B, so this part is B. Okay, so there's more of B and less of A. There's some fraction, and this is the total vapor pressure which I'd be getting. Okay, and suppose that I am over here, that tells me that the container only contains this point. Okay, the container only contains the liquid A, but when I move from left to right, what I see is that the vapor pressure increases, since there is some fraction of the uh, second liquid that is giving some vapor pressure, you know so we reach up to this point, and finally we reach over here, and this is the point at which there is no liquid A in the solution, uh, and we have got the mole fraction of B as the only thing. That means it's 1, and we have got 60 as vapor pressure. But in between these two, it gives you, what will be the fraction of A and B, and what will be the vapor pressure at different mole fractions of A and B. Okay, so we can say that the total pressure, that is pressure total, is equal to the vapor pressure of A, that's 50, vapor pressure of A, plus the difference in the vapor pressure of the bigger one minus the smaller one. Okay, and that extra vapor pressure that we are experiencing because of the part that is more volatile, and over here I've got B that is more volatile, and the mole fraction of that second liquid B. Okay, thanks for watching the video.